Friends, we are talking about chemical reactions here, and let's take a particular chemical reaction where we have iron in powdered form and copper sulfate also as powdered or crystals. And now we want to react these two to give the products of the reaction. We'll have to take copper sulfate in solution for this reaction to happen. Now the question for us is, how much of each reactant should I take? Should I take iron and copper sulfate both in equal weight? So will that give me a better reaction? Or alternatively, should I take equal volume, which means one spoon of each, one spatula of each? Will that give me a better reaction? So we can try doing this, but we have no way of deciding. So here are the two reactants, and the products they give us are these two powders, a light green color and reddish brown color. So light green powder is the ferrous sulfate and the reddish powder is copper or Cu. So the color of products is quite different from reactants, which helps us recognize how much of reactant has been converted to the products. So for this reaction, we have the equation which is telling us that one atom of iron is actually combining with one molecule of copper sulfate to give one molecule of ferrous sulfate and one atom of copper. So we know about the numbers of particles reacting with each other, how one particle each of these react. But can we say something about their weights as well? Do we know something about weights or masses here? So the equation tells us in terms of atomic masses. Atomic mass is measured in the unit of mu or U, which is a very small unit with which we measure atoms. So oxygen in this unit is 16U, sulfur is 32U, iron is 56U, and copper is 63.5U, which is actually in fractions simply because many types or isotopes of copper are mixed with each other and their average mass is taken. So therefore 63.5 is taken as the unit even for an atom. So now using these atomic masses, we get the equation that 56U of iron actually combines with 159.5U of copper sulfate, which is the weight of one particle, to give so much of ferrous sulfate and copper. So we know this equation in terms of atomic or molecular weights, but these are very small units and we cannot measure them. So to do a practical experiment in reality, we need more convenient units or weights. So we can use some technique, which we will now utilize. What we will do is, now we will first see that 1U is 1.66 into 10 to the power minus 24 grams. This is the relation between the two units. So if it is written in another manner, 1 gram becomes 1 upon 1.66 into 10 to the power minus 24 U, and this number, this division gives us one very important number, 6.02 into 10 to the power 23. So 1 gram is equal to this number into U, and this number is called the mole or Avogadro's number or Na, or sometimes L is also used. This is a very important number and extremely useful. This number mole is very useful because it's a unit multiplying number. When we want to change units to larger values, convenient values, so we can write that 1 gram is Na times 1 atomic mass unit, 1U. So this is the relation between the two units, and Na is the multiplication factor The way we use dozen and other multiplication factors, so when we say 1 dozen of something, it means 12 of that thing. 1 dozen unit is 12 of that unit. Similarly, kilo, if I write kilo against something, so 1 kilometer is 1000 meters, so it multiplies by 1000. So similarly, 1 mole atoms means 6.02 into 10 to the power 23 atoms. So anything with 1 mole becomes multiplied. So mole is a number. It is not a unit, but it's a very convenient number. So here we have our equation where we have atomic masses of all the reactants and products written under the equation. So, and since we cannot take such small units or such small quantities, we multiply each side, the whole equation, by Na or the mole. So we take Na times everything given here. So this automatically converts it into grams. So because U into Na gives me grams, so therefore the whole equation gets converted into grams. The atomic mass is written, and again with that gram is written, and which gives us a huge benefit of changing everything into very convenient units of grams. So I can take 56 grams of iron and then make it combine with copper sulfate in again 159.5 grams, which is measurable for me, to give so many grams of the products. So the whole equation gets converted into very practical units which we can use in reality. So this is also called the mole. So we say we have taken 1 mole of iron and 1 mole of copper sulfate, which is the atomic mass written with grams. So conversion into mole simply means we take the atomic number and write grams with it. So 1 gram mole or gram mole of any substance is actually the atomic weight written in grams, which also means that this weight has a certain number of fixed number of particles, which is 6.02 into 10 to the power 23 number of atoms or molecules. So I know the number of particles as well as I know the weight that should be taken. So both gives me a very powerful tool. So we can see that now when we are taking reactants, so we can make a choice. Should we take them equal in mass, or should we take them equal in volume, or should we take them equal in moles? And we can check and see which of these strategies gives us the best results. So let us see this using a practical experiment, the experiment we were talking about earlier. So here we have equal weight of iron and copper sulfate, and because equal weight, so we have written W for it and we have taken 0.5 grams of each. Here we have equal volumes of each, so we have taken 1 small spoon of each iron and copper sulfate, and therefore V written here. And since this is equal moles, we have taken equal moles of each, and 1 mole is 56 grams, so that is very large, so I have taken 100, 0.56 grams. Similarly, 1 mole of copper sulfate is 159 grams, so here we have taken 1.59. That means 100th of a mole of each reactant is taken, and we have written M to show equal moles. So in the 3 beakers we will do the experiment, and for that we will first dissolve the copper sulfate in clean water and also heat it a little for the reaction to happen faster. So now I am adding for M, the beaker M, I am dissolving copper sulfate here, heat it a little, and I have also added the measured iron, 100th mole of iron. So 2 reactants are mixed now, and with a little bit of heating we will get the experiment. We will do the same thing with the other 2 quantities also, equal weights, equal moles and equal volumes. So all the three experimental results are here, and in the fourth beaker we have kept pure copper sulfate just to compare the color. So let us check the results in each case. So in equal volumes, if I can see the color of the product ferrous sulfate as light green, but the color of copper is not visible. And here I am testing with a magnet and I see a lot of iron left over. Its color is black, but also it is being attracted by the magnet. So the reaction is not complete and much of reactant, one reactant is left. Similarly, in equal weight category, I am again seeing ferrous sulfate, but when I check for iron, again I find a lot of extra iron here which has not reacted and which is responding to the magnet. Now in the third case, which is equal moles, the M beaker, now we see both colors here, both products. I see light color of copper sulfate and also copper. If I move the magnet, I see some movement, which means some iron is still left. The reaction is not generally 100% complete because of presence of iron oxide, but still here the maximum amount of copper has been generated in this beaker as compared to the others. Much less iron is left and far more copper is generated. So the best reaction has happened in the third case.